Chapter 8, Alkenes, Introduction. Based on what you guys know from functional groups, an alkene looks like this, where this is a pi bond and this is a sigma bond. An alkene only have one pi bond. That pi bond could act as a nucleophile or base. So if I mix this alkene with an XY reaction, there's nothing labeled for XY, it's just an example. The pi bond would do the attack. This is the mechanism. The pi bond would break and result in, first of all, X get added to that side and then result with carbocation on that side. You're left with Y, and Y have a negative charge in this case, would act as a nucleophile and would attack here. The resultant is so in 8.3 we're going to talk about the thermodynamics of an alkene. So in this we'll use a real example. Here I have an alkene, and I'm going to add it to hydrochloric acid, and I'm going to see what it's going to give me. Remember from 8.1 how we said pi bond could act as a nucleophile or base. In this situation, would act as a base, would actually extract that hydrogen. I'm not going to really draw the whole mechanism, but I'm going to just give you the result. The result should be like this. Remember, one attached to that side and the hydrogen attached to that side. Okay, so if I go from the reactant to the product, that is called addition. And that's what mainly this whole chapter is going to be about, addition of an alkene. And if I go back from the product to the reactant, if you guys remember from chapter 7, this is to form an alkene, this is an elimination. So which one is right? Which one would give me an addition? Which one would give me elimination? How would I know? Thankfully, we have the Gibbs free energy, right? Which is delta H minus temperature multiplied by delta S. Or delta S is your entropy. Delta H is your enthalpy, and T is your temperature, right? So delta H, if you remember, is the sum of bonds broken minus the sum of bonds formed. And delta S is which one is more disorder or less disorder. We can tell because we're going from two reactants to one product. This is less disordered, so we remember less disorder give us a negative delta S, negative entropy. But let's count the delta H. I have 63 for the alkene. I have 103 for my hydrochloric acid. I have 101 for my addition product, and actually, sorry, the CH bond is 101, the CCl bond is 84. Right, if I do the sum of it, it would be, my delta H would be 166 minus 185, which would give me negative 19 kcal. So my delta H is negative, my entropy is negative, my entropy is also negative. In this case, for it to be spontaneous, I have to be at low temperature. So I know addition at low temperature, well, the reaction at low temperature would be spontaneous, would give me an addition. And the vice versa, at high temp, I would go back to elimination. And that's why alkenes are beneficial, because I can control them from elimination to addition just based on temperature. Section 8.4, we're doing hydrohalogenation, where we're adding hydrogen and a halogen to an alkene, the halogens in this case would be bromine, chlorine, iodine. We're just going to ignore fluorine for a second. We have two types of an alkene. This is the first type, symmetrical alkene. So we have an alkene, we're adding it to hydrochloric acid. Just as we remember from 8.1 and 8.3, the pi bond could act as a nucleophile or base, and so we'll do in this case. That pi bond would take that hydrogen away from this chlorine, and that chlorine would come and attack again because it would be negative. Anyhow, the result would be something like this, where chlorine get added to one side and then hydrogen get added to another side. And in this case, you really don't care about whether where the halogen is going to get added or the hydrogen is going to get added. But in this you will. Our second case, which is asymmetrical, recall alkene, which we have an example of this, and I'm going to add it to HBr, and we'll see what the result's going to be as. I'm going to draw the full mechanism for you, because in this case you need to care, in asymmetrical you need to care where the hydrogen is going to get added and the bromine is going to get added. So this pi bond would come and attack this hydrogen, extract it from that bromine is going to be left alone. So I'm going to show a mechanism right here. Hold on a sec. After this takes the hydrogen, the pi bond would break, so you're left with this, right? So the carbocation could be formed on either this carbon or that carbon, both ends of the alkene, of the pi bond. So if I put it on this carbon, this is a tertiary carbon. Or if I add it, versus this is secondary carbon. Which one is more stable? Of course, we learned that tertiary is more stable. So the halogen gets added to the more substituted side, and that will give you the Markovnikov addition. Markovnikov addition, where hydrogen gets added to the least substituted side, and the halogen gets added to the more substituted side. So the product of this would be as that. And here's my hydrogen. As you can tell, hydrogen get added to the least substituted side, and the halogen got added to the more substituted side. This is called the Markovnikov addition. And you can know that it's Markovnikov addition just because of your reagent. This reagent, HBr, HCl, HI, would give you a Markovnikov addition. So for the anti-Markovnikov, for the also asymmetrical alkene. So here's my asymmetrical alkene, and I have this reagent, HBr, and I have peroxide. ROOR is peroxide. And you can tell there's anti-Markovnikov because of this reagent. Remember, if it was HBr by itself, it would have gave you Markovnikov addition, but now HBr as the first reagent and then put also with peroxide would give you anti-Markovnikov. What anti-Markovnikov will do, for now you don't really need to know the mechanism for it, but anti-Markovnikov, remember how like here we had the bromine, which is the halogen, get added to the more substituted side, and that is the Markovnikov. The opposite is for anti-Markovnikov. The halogen would be added to the least substituted side. And if we look at here, this carbon, this end is tertiary, while this carbon is secondary. This is the least substituted side. The halogen would get added to this side. My result would be as, and here's my bromine, there's my chlorine, and the hydrogen. We usually don't write it, but if you insist on, then the hydrogen would be here. And this is called the anti-Markovnikov, where the hydrogen get added to the more substituted side, while the halogen get added to the least substituted side. I've got two examples, and volunteer to solve these examples. I'll do them. There you go, Motaz, good student.
All right, so for the first example, I can see that there's peroxide in the reagent, so that tells me that this is an anti-Markovnikov. And what that means is the hydrogen is going to attach to the more substituted carbon on the alkene, and the bromine is going to attach to the less substituted carbon on the alkene. And so this gives me this result right here. I would get hydrogen on the more substituted, which would be right here, and I would get bromine on the less substituted, which would be right there. Now, for the second example, I don't have peroxide, so I know that it's just Markovnikov, and so that means that the hydrogen is going to attach to the less substituted carbon on the alkene, and chlorine will attach to the more substituted carbon on the alkene. So you go ahead and write that. So hydrogen, again, to this carbon. And now for the chlorine, which would be on here, I noticed that this carbon is chiral. And it's chiral because it's attached to obviously 4 different connections. And so let me just make that a little bigger. So because it's chiral, we have to show stereochemistry. So it would be like so. And I would also get, it would be 50% this and 50% like that. So you have to show that in enantiomer as well.